Okay, now we get to my favorite one. This is adiabatic processes, okay? Adiabatic just means that heat doesn't flow, okay? So Q is 0. So we've got this formula, Q equals delta U plus work, and this guy's 0. How does it happen? Well, you can either just insulate this so that no heat flows, that's not common, right? Or you can just do it quickly. So it's either insulated or it just happens quickly. And these happen all the time. These are ubiquitous. You'll see the effects of adiabatic compression. Any process that's happening fast is going to be largely adiabatic, okay? So it just happens quickly. There are other cases, so we'll look at some other examples here, right? So no heat flows in. If you look at the thermodynamics of this, if that's 0, right, this is an adiabatic expansion, so the work is positive. So therefore, the change in internal energy has to be negative, right? So if the process does positive work, the gas has to cool down, and the question is, how does it cool down, right? Because remember, change in internal energy is intrinsically tied to temperature, okay? So if this goes down, the temperature has to decrease. So the question is, how does a moving piston that's expanding like this, okay, how does that cool the gas down physically? And here's how it happens, right? A particle coming here hits that piston, but since the piston's moving away from it, it's a bit like sort of trapping a soccer ball, right? It comes off with a slower velocity. Here it's fast. Here it's slower because the wall is moving away from it, okay? So physically, thermodynamically, macroscopically, it has to cool because the gas does work. The energy has to come from somewhere. Since no heat flows in, the gas has to cool. Microscopically, particles bouncing off a wall that's moving away come off slower, right? Okay. Now, examples of this. The air rockets, I'll show you a picture of this, right? I don't know if you remember when our air rockets went off, they make a little puff of condensation. They get cool because that was a very rapid adiabatic expansion. The cold side of the fridge, okay? That's how refrigerators make cold. They allow a gas to expand. And then, of course, the universe is remarkably adiabatic, right? Because there's nothing else but the universe. And so the universe started off fiery hot, and as it expanded, it got cooler and cooler. This was an adiabatic expansion. And the temperature of the universe is right about, I think, 2.7 kelvins or something like that. You can look it up. But it's just about what it should be for the expansion that occurred, which is kind of cool, you know. All right, so let's look at some more examples of adiabatic expansions. I'm going to show you this demo in class. Hopefully you'll be, properly impressed. But here it is all right there, right? So this is Emma launching off a rocket, and notice the rocket has just gone off. There it is, right? That's a great shot. But notice that little cloud. See that cloud right there? That's from adiabatic expansion. This gas cooled down to below the dew point. It cooled down, which is kind of cool, right? There's a big word for this type of cloud on there. So this is an airplane breaking the sound barrier, and this is the shock wave. And so right in front of this is a compression, and then right behind it is a rarefaction. That is, it goes from high pressure to low pressure. The gas cools. This is probably near the ocean, okay? The gas cools and condenses. So what we probably would see down here is, the ocean waves, right? Okay, so that's cooling down and condensing, which is kind of neat, right? And you can see when you watch rockets take off, they go through when they break the sound barrier, you can see this little cloud. And then let's look at adiabatic compressions, right? Well, with an adiabatic compression, this is 0, okay? And we do work on the gas, okay? So remember, as we move in, delta, the change in volume is negative. So we have a negative work done. Therefore, if it's got to add to 0, we have a positive change in internal energy, okay? This means that it gets hotter, because remember that internal energy and temperature are intrinsically related, right? 3/2 nRT. So if U goes up, temperature goes up. So the question is, this is macroscopically why pushing the piston in has to make the gas hotter, okay? Microscopically, if this piston's moving in, if it's moving this way, a gas particle bouncing off of this is going to come off faster. So it's going to be slower here, faster here. And the reason for that is because the piston's moving toward the particle. It comes off going faster. This is like in soccer, you're not trying to trap the ball and slow it down. You're trying to get it to the other end of the field so it comes toward you. Well, you kick that ball. You move your foot toward the ball and just clear it. It goes faster. Okay. So adiabatic compressions heat up. They heat up things, and these happen all the time too. Examples: your bike pump. You pump up the tire. The bike pump is hot. Diesels actually heat. They compress the gas to the point where it's white hot, and then I'll show you this. Right? And then they inject fuel in there, and it explodes. No spark plug needed. Okay. All fridges, you know where the cold side of the fridge is, right? That's where the food is. There's also a hot side of the fridge. Okay. So of course that's the game the fridge plays, right? Is that it does adiabatic compression outside the freezer box, adiabatic expansion inside the freezer box. It's clever, right? And then compressors get super hot. I will light a piece of cotton on fire with air. Okay. I want you to be properly impressed when you see it, ooh and ah and everything like that. Here's a compressor. Notice these little air fins on there to cool this thing off because it's compressing the air. That's another picture of air fins. Okay. This is a diesel engine. Diesel engines have super compression ratios, right? More than a gasoline engine. Okay, and that's because diesel fuel is less volatile than gasoline, right? So what they do is they compress this piston moves up, those air particles, just like a ping pong ball bouncing around in there. If you can imagine, as you push that up, the ping pong ball moves faster and faster and faster until the point where if we inject fuel into this space, this white hot air, it explodes. And of course, you got to do that at just the right moment, 3 degrees before top dead center or something like that, right? And that's how a diesel engine works. No spark plugs needed. You just compress that, and the air gets white hot because of the compression. And of course, a cold diesel engine is kind of a bear, right? Because the compression, some of the heat flows into the engine block. So we have little heaters called, what are they? Glow plugs, right? You got to warm up those pistons. So then, let's look at the whole process here, right? We've got a compressor. It compresses the gas. That heats it up. That's an adiabatic compression, which causes a high temperature. The heat flows out all across the back of the fridge. This is an old refrigerator, by the way. New refrigerators have the high pressure side, the hot side underneath the fridge, and they just blow warm air out that way, right? But this is passive. It's just got passive, right? Then it's got a little expansion valve. It expands into the freezer box, and that drops the temperature to super cold. So this is the low pressure side, right? Low pressure side comes back to the compressor. And of course, you got to do work to do this. This is a heat pump. It's pumping heat from actually the cold side here out into the room. And then this also, atmospheric scientists look at this too, right? If you take a chunk of air and you raise it up, it expands. As you raise it up, it expands and gets colder. And this is why it's generally colder as you go up, right? It's, that's why you're cold on airplanes, right? They're flying at 30,000 feet to take advantage of thinner air. So it's cold outside, right? The top of the mountain is colder. It's reliably cooler up in the mountains, right? And then if you take that same air parcel and make it go down, it's going to compress and warm. That's adiabatic compression. It might not be totally purely adiabatic. It might be heat flow, but anyway. So I think that's enough talking about This is the fun thing, right? Now, just, foreshadowing. On this thing, we can't use really the combined gas law or anything because the temperature changes, but we do know this. This is in the data packet. For an adiabatic process, we've got this formula that we can use. And we'll look at that more later, but this basically is sort of like the combined gas law for adiabatic processes. And what the 5/3 does is it makes the volume more important. because, of course, as you decrease the volume, the temperature rises, which causes an additional increase in pressure. And as the volume decreases, you have a temperature drop. Okay, so that sort of takes that into account. I think I'm going to stop talking about adiabatic processes.